as usual, the paper we read papers not only from our SIGCOMM conferences but also from journals or other top tier conferences papers. So this week I think this is the since the starting of this activity, this is the first time we read a paper from a journal. So this is a very fresh paper publishing from ACM Computing Surveys. And we have focused, because in the past maybe 11 or 12 meetings, we have covered many aspects of computer networkings, in particular the verification, how to design more efficient RDMA networks, and how to diagnose anomaly in the system, and how to do wide area interdomain data collection and analysis, and so on. Lots of different aspects. So this week we decided to pick another topic which we haven't covered before in our meeting. This area is network telemetry. So the paper we select is titled "Compact Data Structure for Network Telemetry." So this is a more like a position or survey paper by Shir and Zaoxing Alan, and also Jennifer Rexford. So it's a very comprehensive survey about data structures that can be used or have potentials in network telemetry. So as usual, we will have a volunteer to present this paper, but this is also the first time we did not have a student present the paper, but instead we have Dr. Tang, an assistant professor from Xiamen University, to present. And for two reasons. First, Lu is an expert in Sketch and network telemetry, and second, because we feel this is a survey paper, has visions, has positions. So we figured maybe a junior student may not be ready just yet to present such a paper, to convey the key ideas and the position of this paper very comprehensively. So that's why I suggest Lu do the presentation, and she's very generous to take the time to prepare the presentation. So so this is a very brief opening. So as usual, we will leave the floor to Lu to present this paper for maybe about 25 or 30 minutes. And after that, we will have Shir and Alan, the first two authors of this paper, to join us for a live discussion. Okay, so I think this is a very brief introduction. So Lu, you can get started. You need to unmute yourself. Yeah. Lu, you need to unmute.
Okay, sorry.
Yeah, we can hear you now.
Thank you for your introduction, Chao. And now I will present the paper Compact Data Structures for Network Telemetry. And this is a joint work from the Open University of Israel, University of Maryland, and Princeton University. I'm Lu Tang from Xiamen University. It's my great honor to present this paper. Network telemetry is an essential way more efficient. Traditional traffic measurement such as SNMP or net flow, they only provide high-level information. For example, SNMP only supports link-level statistics on the timescales of minutes, and although net flow supports core flow counting, however, to maintain efficient memory usage, net flow also often maintains a very small sampling rate to track only a small portion of flows. Hence, it has low accuracy in high-speed network. Also, these traditional approaches have slow reactions because they have high delay for analyzing measurement data. This makes them unable to support real-time telemetry tasks such as detecting microbursts. More importantly, this approach cannot be customized, and operators can only use the information provided by these approaches, and they cannot customize how to measure the traffic. The emergence of programmable network device provides great opportunities for more efficient network telemetry. And here we take programmable switch as an example. And in traditional switch, the data plan is supported by fixed function chipset, and users cannot control how the packets are processed. In contrast, in the programmable data plan, users can write program to customize the processing logic of package. And this program can be written by domain-specific language, such as P4. So with programmable network devices, network system developers can take control of how packets are processed. And with this programmable data plan, now we can customize telemetry by specify what information we want to collect and customize how we want to analyze this data. And also, we can customize how to react to the measurement results. The representative programmable data plan is the protocol independent switch architecture. And this architecture contains three components. And the first component is a programmable parser. And users can write program to control how their package header how to extract the packet header information. And then after that, the package will go into the match action pipeline. And this pipeline contains the match logic and action logic. The match logic has from and tcam for lookup tables, counters, and hash functions, while the action logic has ALUs for bit and arithmetic operations. After that, the package goes into the deparser and then be forwarded. And with the programmable data plan, now we can perform programmable packet processing. And once the package enters into the switch pipeline, it first goes into the programmable parser. And in the parser, we can determine the tuple of fields extracted from each package. And then we can match on these fields to group related packets into a single flow. After that, based on the matched results, we can perform computation such as hash, arithmetic, or logic operations on the package, and we can also store these computation results and informations across successive packets in the register arrays, and this enable more complex operations over multiple packets. And finally, the control plane can report the results to the data. The data plan can report the results to the control plane and let the control plane to read and update its states. With the programmable data plan, and we now can perform high-speed programmable packet processing, and the programmable data plan provides good visibility into the network, and we can customize how we can customize the telemetry logic in the data plan. However, the programmable data plan poses significant resource constraints. For example, it contains only tens of megabyte memory, and it has limited ALU capability. For example, it supports only simple hash computation and simple addition, subtraction, and bit shifting. Also, the programmable data plan has limited memory access. It allows only one memory access for each package for the same register array. So if we want to deploy telemetry applications in the data plan, these applications must meet the resource constraints. Fortunately, most telemetry queries requires only approximate answer. For example, for a load balancing application, operators cares more about which flows are heavy instead of the exactly package counts of those heavy flow. Compact data structures provide us such approximate answer with efficient memory usage. The classical compact data structures such as count-min, bloom filter, and space saving. These data structures process data in a one-pass manner, and they provide probable error bounds. And more importantly, they are compact. They use sublinear or even logarithmic memory usage. With these features, compact data structures are inherently fit in the data plan. So in this paper, we will review compact data structures in programmable network hardware. The goal is to highlight the challenges and considerations in creating and using them within programmable devices. And based on this discussion, the paper further discusses promising directions for future research. In the following, we will introduce these three topics. And the first topic is how to deploy compact data structures on a single network device. Based on this, the second topic discusses the resource optimization in the data plan. And finally, we will discuss the distributed telemetry. Before we go into the detail of the first topic, we first introduce the background of telemetry queries. And in network telemetry, we take each package as a tuple of header fields and attributes. Header fields can be any combination of fields of interest, such as source IP, and the attributes can be packet size or other related metadata information, for example, timestamp, location. And we take a flow as a set of packets that has the same flow key. Here, flow key is the combination of headers defined by users. For example, we can define a flow as a set of packets that has the same source IP. And flow telemetry query is to calculate metrics on the flow's attributes. And here we use an example to illustrate the relationship of packets and flow telemetry query. And on the left, we have 5 packets, and we denote each packet as 5 tuple fields and packet count. And on the right, we have 2 telemetry queries. In the first query, we defined a flow. We defined flow key as source IP, and we want to know the packet count of each flow. So the for flow 1 and whose flow key equals to IP1, and it has 3 packages with packet count 1. So the packet count of flow 1 is the summation of these 3 packages, and it equals to 3. According to the content of telemetry queries, we can classify telemetry query into 3 classes. The first class is volume-based statistics, and including heavy hitter top K flows and other flow statistics. And Widely used volume-based telemetry queries are heavy hitters and top K flows, and both these queries are about the frequency of a flow. For example, heavy hitters are flows with whose packet count or frequency are higher than a specified threshold, and top K flows are the top K heaviest flows. And both of these queries can support applications such as traffic engineering and load balancer. And another flow statistic is aggregated flow statistic, such as distinct count, quantiles, and entropy. All of these queries are important for attack detection. For example, if we find there are a lot of distinct connections in the network, and it may be an important indicator for DDoS attack. And also, the second class is queries over packet metadata, and this class of queries are related to performance diagnosis. For example, if we query over time step, and we can calculate the round trip time, and this helps us to diagnose quality of experience and congestion issues. And also, we can perform query on windows, and the window can be fixed time intervals or sliding window. And now, all of these telemetry queries are well supported by compact data structures. And these compact data structures, some of them are well fit in the data plan, while some of them need some adaptations to be deployed in the data plan. And next, we will go through these compact data structures. And we first see the flow statistics. We first see the data structures related to flow statistics. And the most well-known sketches or compact data structure is count-mean sketch. And here is the data structure of count-mean. It contains a two-dimensional table, and it contains R rows, and each row has C counters. Count-mean sketch is used to identify heavy hitters, and for each flow, count-mean first hash the flow into one counter per row. It then increments each hashed counter by one. And count-mean returns the minimum value among all hashed counters as the estimated count of a flow. And from the update procedure of count-mean, we can see that count-mean contains simple computation, only simple hash and simple count. And also, count-mean has small memory footprint. It has one memory access to each row. And these features make count-mean well fit in the data plan. And we can directly deploy count-mean in data plan just by implementing each row as a register array. And the next classical compact data structure is Bloom filter. Bloom filter is used to support membership queries. And for each flow, Bloom filter hash the flow into 3 positions in the bit array and set all hashed positions to 1. And if the hash position of a flow are not all ones, it means the flow is not in the Bloom filter. And we can see that the computation of Bloom filter is also simple. However, Bloom filter requires multiple access to the same array, and this makes it challenging to deploy in data plan. And we need some adaptation on Bloom filter to deploy it in the data plan. And we can just simply separate the 1-bit array into 3 separate arrays and perform each array independently, just like CountMe. And this implementation ensures error rate no higher than the original Bloom filter. And space saving is another compact data structure which is used for top K to identify top K flows. And space saving has a little complex update procedure. It contains a single array with K buckets, and each bucket has 3 components: key, counter, and error. And to update space saving, it first check if the current flow is already in the array. And if it is not in the array, space saving will kick out the smallest item and insert the flow X. And from this update procedure, we can see that space saving requires go through the entire table to search X and to find the minimum item, and it violates the memory constraint of the data plan. So we cannot deploy space saving directly in the data plan. However, some work that focus on improve space saving to make it more hardware feasible. One representative work is precision, and precision just split this single array into multiple independent array, and by find the minimum item among OD hashed counters, and precision prevent to traversing the entire table, and thus make space saving feasible into the data plan. And another example is count distinct, and linear counting is a sketch to calculate the cardinality of the data stream, and its update procedure is also quite simple, just hash and a simple count. However, its cardinality estimation requires complex computation such as multiplication and division, and this makes linear counting unable to be deployed in the data plan. And Boku transform the complex computation of linear counting into a coupon collection problem. It just collect coupons which only involves simple arithmetic computations. By doing so, Boku can count distinct with threshold directly in the data plan. And except for those compact data structures, and there are also some complex sketch designs that support multiple metric. UniMore and RHH are examples in this category. And UniMore, here is its data structure. It contains multiple levels of sketches. And to update a package, it requires at most log n sketches. It requires at most log n updates. And this makes UniMore unable to be deployed in data plan because it has excessive hash count and memory access. However, previous work SketchLab focused on optimizing sketches in the programmable data plan. It proposed multiple correctness preserving optimizations and successfully deploy UniMore in the data plan. Another example is RHH, and also RHH contains multiple level sketches, and SketchLab by optimizing the design of RHH, SketchLab can deploy RHH in the data plan. Different from RHH and UnitMod, Cocoa Sketch are dedicated for are designed for the data plan. And the main idea of a Cocoa Sketch is that it just put simple sketch computation in the data plan and put the complex analysis in the control plane. And in the data plan, Cocoa Sketch just collects package counters like count min. And in the control plane, Cocoa Sketch just recover the full key table and then support arbitrary flow key queries. In addition to the data structures that support flow statistics, there are also some compact data structures support performance statistics. And different from the flow statistic-based sketches, when design performance statistics sketches, there are two main challenges here. The first challenge is cross-package dependencies. In the volume in the flow statistics, in the flow-based sketches, we process package independently. However, in performance, when we collect performance statistics, we require cross-package dependencies. For example, if we want to measure the round-trip time, we need to subtract the receiving time of the request package and the receiving time of the reply package. And this dependencies makes it challenging to design and deploy compact data structures in the data plan. Another challenge is that previous work has proved that it is infeasible to compute such performance metrics in sublinear way. So the above two challenges motivate the design of new non-sublinear algorithms. And these algorithms need to consider two questions. The first is how to efficiently store information of previous packets. And the second question is how to avoid bias in the estimation. And one example is Feibish. Feibish is a sketch design for the data plan that to track the round-trip time. The round-trip time can be calculated by the difference of the transmission time of the request package and the receiving time of the response package. And the naive approach is we deploy a hash table in the data plan, and the data plan performs per flow counting, and we just record the transmission time of the request package. And when we receive the response package, we just subtraction the receiving time from the transmission time, and we get the round trip time of the package of the flow. However, this naive approach is too resource consuming, as it requires per flow memory consumption. And Feibish solve this problem by introduce probabilistic tracking, and it also introduced a bias correction mechanism to provide unbiased RTT estimation. And the second performance metric is out-of-order packets. And out-of-order packets are packets who come whose time step whose sequence number is smaller than the maximum sequence number observed. And out-of-order packets is an important indicator for the network condition, and it helps us to infer incorrectly configured QoS problem. And some work focus on tracking out-of-order packets in the data plan. For example, Lean algorithm transform the poor flow tracking problem into find flows with high number of out-of-order packets. And this allows Lean algorithm to use sublinear memory to track out-of-order packets. And also prefix algorithm identifying IP prefixes with heavy out-of-order packets, and it achieves more memory efficient. Now we go into the second topic, that is how to allocate resource among network telemetry tasks in the data plan. And we first see the common steps to deploy a telemetry task in the data plan. And the first step is user specify the telemetry task and the required accuracy to a compiler. And the compiler outputs the which compact data structure to use and its parameter settings to satisfy the requirements of users. And here we need to address one important problem, that is how to quantify the accuracy as a function of the memory usage. And this is a key problem the compiler needs to solve. And we have three ways to do this. And the first way is to use the theoretical error bound of the data structure. For example, we take count_min as an example. If we set the parameter of count_min as this, and then we can get the error bound of count_min. That is the probability of error larger than epsilon s is smaller than delta. However, the analyzing the theoretical.
Sorry to interrupt. You might want to speed up a little bit. I think because we want to leave plenty of time for discussion.
Okay. This way has theoretical practice gap problem because it is based on the worst case analysis. And the second method is to simulate representative historical traffic traces. And however, this method it is uncertain to how long of a trace to use, and it is uncertain to the impact of traffic shifts. And also we have method 3 to design self-mirroring data structures. And these data structures can report the estimation error in the runtime. And this is a very interesting topic for the future research. And also, we can optimize resource allocation. And usually, we formulate the resource allocation among multiple telemetry tasks as an integer linear program. And by solving this IRP problem, and we can get a good configuration. And also we can use some work explore the statistical multiplexing advantages among data structures to improve memory efficiency. And also some work focus on explore division of time across queries. And also, even if we optimize the resource allocation in the data plan, and the resource of the data plan may still not sufficient for queries. And in this situation, one common approach is to partition a query to run partially in the data plan and partially in the control plan. And the last topic is distributed telemetry. And as network problem often spread throughout the network, so we need to deploy our telemetry task in a network-wide manner. So the first problem is how to how to place our measurement task. And some work focus on this problem and propose many approaches to optimize task placement. And the second problem is how to decide the aggregation rate, and all the measurement results at each measurement point should aggregate at a central controller. And this aggregation rate is it can affect accuracy if we report more frequently, and we can get more accurate results. However, it incurs more communication overhead. So some work focus on addressing this problem and propose probabilistic reporting to achieve a better balance between accuracy and communication overhead. And also in distributed telemetry, and another case is path-based monitoring, and the representative is in-band network telemetry, and it lets the package itself to carry the measurement information, and Pint optimize int by propose probabilistic int, that is, the package can carry the measurement information in a small probability to reduce communication overhead. And also, another case in distributed telemetry is intra-switch distributed telemetry. This is because some telemetry tasks, such as to monitor the loss or delay in a switch, requires the intra-switch statistic, and it requires the pipelines of the switch. It requires to merge the measurements across pipelines in the switch. And also, many work focus on how to more efficiently merge these cross-pipeline measurement results. And in summary, the programmable network devices provide us high speed and good network visibility, and it provides opportunities for more flexible network telemetry. However, it has significant resource constraints, and the compact data structure can bridge the gap between various telemetry pairs and the program network devices. And based on and there are also some interesting further directions in this area, such as design compact data structures to support more complex queries, or support multiple queries concurrently, and also how to efficiently collect the queries at multiple measurement points at runtime is also an interesting direction. And this is all about the paper. Thank you.
Cool. Yeah. Thanks, Lou, for the presentation. I know it's a little bit lengthy because this is a relatively longer paper. So I really appreciate the presentation. I think it's a quite a comprehensive tutorial. And I think for our fourth semester, we can even use the recording as a lecture to teach students about the telemetry and sketch and all kinds of these data structures. So now we move on to our discussion. So I know, Lou, you have done a lot of research in this area as well. So you must have your own questions. You want to throw these questions to Shir and Alan to jumpstart the discussion.
Yes. My first question is that in traditional data center networks, the traffic are highly skewed, and this character makes us to enable us to only monitor a small fraction of flows to make us focus on only the heavy flows. However, in the AI clusters, the traffic pattern are changed. For example, in AI clusters, the traffic have low entropy. And my question is, how to design new compact data structures for AI clusters?
Shir, do you want to go ahead, or
you can start if you want.
So I think, thank you very much for this presentation. I think it summarized the paper well, but I think this problem is probably, I think, more trendy in terms of AI workload monitoring, right? As a telemetry, of course, we have to monitor all kind of traffic. AI traffic is one of the thing. So you mentioned that in terms of skewness, right? Like, the traditional flow-based monitoring could be based on the assumption that we have some flows are very large, very frequent, that become high entropy. But in terms of AI workloads, that my team are doing a little bit on the collective communication, right? So I think there's a two consideration we can think about along these lines. Number one is that in the AI workload, especially on the collective communications, is the flow-based monitoring still the right model to kind of monitoring this kind of workload? Is that we should kind of based on, for example, the message sizes of each collective, that some are like all reduced, some are, all gather, some are, and some other kind of collectives. Is that we should kind of think about different model of monitoring in terms of this traffic, instead of I have monitor every packet and every five tuple for that. I really doubt that, right? So I don't think that this traditional 5 tuple would be the right model to monitor that. The second, even that is the model that we should consider. Then it is maybe we need to kind of think about, hey, we have multiple different platforms to pursue this. Like we in this particular survey paper, we're talking about hardware focus on switches, but I think the AI workload, they may not be the only places we do monitoring, right? And as far as we know that even a lot of the production level networking on the AI training workload, some are using NVIDIA's network, right? It's a proprietary Mellanox networks, right? It's very hard to customize anything on that switch level, but it is possible to customize on the NIC and still at the host level. That could be promoting a lot of design that it's more optimizing the processing speed. We still wanted our data structure to be lightweight, but may not be as constrained as that we have to fit everything to a switch only has several megabytes, right? We can kind of balance between, like, we want to collect at a very low weight, and also memory is smaller, but it's not like, hey, we have to consider extreme cases that we have fit 500 kilobytes or 5 megabytes. That's my kind of thoughts on that.
Okay, thank you.
So just to continue on what Alan is saying. So first of all, Lou, thank you so much for the great presentation. This is not an easy paper, I think, to present, and you did a really good job. So thank you for that. To continue on what Alan is saying, I think that we will probably see more telemetry that combines, for example, NICs along with switches, and have some collaboration between the different targets that we have in the network, which would probably help us in doing telemetry where it is best to do the telemetry, and not just decide based on whatever. For example, if we don't have access to the NICs, then we're left with the switches, essentially. And for the other thing that Alan started out with, I think that one thing that has not been studied much is this. So if we're not doing like per flow telemetry, another option is to do group telemetry. For example, can we identify the groups of a group of flows that is actually heavy, or things along those lines, which I think hasn't been studied much, but I think will definitely be relevant in these kind of cases.
Okay. Thank you. I have another question. Is that in performance diagnosis, And I think they require more accurate telemetry results. And for example, if we want to detect packet loss between, for example, between two switches, uplink switch and downlink switch, and we need the counter to be accurately. However, the limited memory resources and if we use compact data structures and they only provide approximate results, and even the error is very small, and the error can still can cause us errors on the packet loss detection. So how to address such situations, that is how to design or perform telemetry in situations that has a significant requirement on accuracy, even zero error situation.
So I think there is an inherent trade-off here between the amount of resources that we can use and the accuracy, or the amount of tasks, or the type of tasks that we can perform. I think one thing to think about in these kind of cases is going back to another paper of ours, which basically looks at packet loss in a switch in a reactive monitoring setting. So if we can identify when or where even we need to perform specific measurements, then we can use the resources more wisely, and then we can improve accuracy in order to, in the cases where we're only monitoring where it's really needed, then we can allocate the resources accordingly and then improve accuracy because of the added resources.
Okay.
Yeah, I think it's a very interesting take, right? So in many cases, we might want to guarantee something that's perfect accuracy. It depends on what we need, right? So, either we relax the memory requirements, or we can, I think it's interesting to kind of new type of data structure where, for example, it's not like you have a perfect guarantee for every flow, then it's a deterministic data structure, right? If you want something approximate, can you at least guarantee something that is, for example, the largest flows, we can guarantee that it has, perfect accuracy. Some other flows are, smaller group of flows are, we don't have guarantee for that flow. I don't see anything like that, but I think it's a data structure field that they have something called self-repairing, like a filters or something, like, if they find the errors on certain this type of flows, and they can kind of improving this kind of data structure by removing these errors continuously and then improving the data structure. But it's not guaranteed that it's always correct for all, but it can help correct the accuracy for some importance or VIPs that you define, right? And along these lines, could be also this kind of definition can be leveraged, especially for, like you say, network performance, and what are the VIPs you define, and we can kind of devote more resources for that kind of group of flows.
Okay, thank you. I have another question. I have read your paper that you have coordinated heterogeneous programmable devices and to support telemetry tasks. My question is, can we coordinate these heterogeneous devices at runtime? For example, we have a set of telemetry tasks, and I need the compiler to tell me how to split or deploy my tasks in the network. Maybe some are deployed on DPU, or some are deployed on a switch data plan, and even on the end host. Can this decision be made at runtime? And can I adjust my deployment decision at runtime?
So I assuming that you're talking about the Shir sketch paper we wrote before, or it's another paper. So,
Yes.
Yeah, go ahead. So I think this is a great question, right? I think the ideal world is it's basically has two factors. One is that why we need to do its runtime configuration. We wanted to get most accurate monitoring over best possible resource allocation, right? That could be because of that the workload can always change, and then the best possible configuration can be always changing. The second thing is that is it possible for all the vantage point that we can deploy these measurement points, right? Like in the old days that Intel switches and some switches, the Cisco switches, you can customize something, right? But you cannot customize at the runtime of, for example, seconds. Every second you reload your firmware or change the software. It's very hard to do so, right? So I think currently my answer is very hard. It's possibly near runtime is possible. But if you talk about, hey, it's pure software that we do everything on software on NIC or N hosts, I think it's possible on doing this runtime kind of reallocation. And I think there's still a lot of room to optimize in that domain, right? So like your compiler, how frequent, how fast your compiler can run, and how fast your data structure can be changed without losing the previous data, right? Do you want to merge from the old data? Are you just completely ignore the old data? All this kind of consideration, that's a critical issue. But I kind of agree with you that it could be an ideal world that we can continuously tuning the monitoring system online, that achieving the best possible guarantee and the lowest possible resource allocation. Right, it's much better than that NetFlow that I set up on a sampling rate, and then I wish for the best that all the issue I can capture by the by a fixed sampling rate.
Okay, thank you. Okay, one more question, and we know, and the compact data structures can support many telemetry tasks such as anomaly detection. One example is DDoS attack detection. However, currently, more anomaly detection approaches are based on machine learning. And my question is, can we combine compact data structures and machine learning approaches together to perform more efficient network telemetry?
So, Shir, do you want to chime in?
Yeah, I mean, I think it's a great question. I'm not sure, actually. I think, so we want things that are more, I think, explainable in telemetry in general, and usually in ML, we don't always have that. So I don't know if we're going to be able to combine these things. I don't know if we're going to be able to use compact data structures for ML. I don't think we're quite there yet. But I don't know. I think it's a great question.
It's a great point, but I think there's a one line of work that applying machine learning to tune the structure that it's achieving the best possible configuration in react to the current workload. I think that is totally explainable, and it's quite interesting in that sense, right? But if you say, hey, I just based on the data structure that we create and then getting that to feed into machine learning models and getting inference results, that part is possible. But as Shir said, I think it's quite a gap there. I'm not sure if we are there yet because of the existing model. I know from like DDoS or anomaly detection, they're more based on the packet level features, like, hey, the size distribution of this, and some small changes on the input data to them. could lead to the, your tree models that has a very different classification result. This is what I learned, right? So they might sometimes even more overfit to a very specific type of attack than a little bit error changes will lead to a result that's unpredictable. I think that part is quite hard to kind of guarantee that, what kind of error will not be a problem, what kind of error is fine. So that kind of thing is a big gap.
Okay, thank you.
I think also if we are able to identify what this traffic looks like, then we might be able to fine tune the structures to look for more specific things, or to somehow change the type of telemetry we're doing to some extent. But yeah, I think this is going to take some time.
So Lu, is it okay I ask 2 questions maybe? Hello?
Lu seems to lost the connection.
How about now? Can people hear me?
Yeah, I can hear you. We can hear you. I think probably Lu lost her connection.
I see. Yeah. So I actually have 2 questions. One is a little bit technical. So because probably Alan know that I'm not really a telemetry person, so my knowledge is very limited. But if my first question is, if we want to compare, we will right now. My understanding is we do a lot of telemetry focusing on more in data center networks. But if we try to expand, try to basically do very accurate and efficient telemetry in wide area network, what would be the most fundamental challenges, 1 or 2? Do you think?
So that's a great point, right? So I think fundamentally, maybe this, the resource constraint, the type of traffic statistics or characteristics of the traffic could be different, but I don't see fundamentally we will need to be different, right? The wide area network could be, each link could be a lower speed or higher speed, but with more limited traffic. More limited resources to be able for you to do telemetry. The second is that the traffic that on a wide area tend to be more like diverse, more low entropy, or something. It's like because of a lot more user, different type of applications. Where in data center, the traffic could be more uniform, more like focus on specific applications, right? I think the major challenge between these 2 settings are more like what kind of traffic look like, and applications running on top of that are different. But otherwise, I think a lot of the insight that we develop for like data center networks should be also applied to wide area networks, right? And should be equivalently useful. Especially that we consider we have a lot of wide area switches that you can deploy sketches to understand the traffic and and the traffic statistics.
I see. So sorry. Sure, you want to say something or?
No, I just wanted to say that. I mean, I think I totally agree with what Alan is saying. I think that it really depends on what we want to monitor for, and the tools seem like they would be useful for the WAN setting as well. Like several years ago, we had a work with that measured congestion in the AT&T backbone network. So that's and we're essentially using the same structures and kind of ideas that we have in use in the data centers. So yeah, I think this is it's really more of a question of what do we need to measure, what do we want to measure, and then how will that help us?
I see. Okay, cool. Yeah, cool. I think I understand. So I have another question, but I think there's also a question from the audience. I think it's Dr. Xiang Chen from Zhejiang University, China. I know Xiang personally, so he's also an expert in telemetry. So his question is, can large language model based sketches or measurement system be built? And if so, how do you vision like a large language model be utilized in these cases?
That's a great question. Right timing for LLM. Yeah, maybe Shir can chime in, but I just have one quick take, right? So I think every domain should think about how this wave of LLM should be used. I was seeing two type of papers that leveraging LLM. One, I think it's a typical use cases where the LLM is always a good interface to translate natural language into different kind of aspects, like traffic configurations or understanding certain based on the sketch result and using this LLM to do even some kind of classification. I think I would see that I would classify that as a use case of interface, like telemetry interface. And then there's also a SIGCOMM paper, I think, experience paper. They use LLM to answer and find what are the queries that to be asked in a large telemetry databases. They may not be sketch, but it's a mix of sketches or NetFlow and other data they store. I think this is also an interface. A second class, I can think about it. What if we start building this provable data sketches with and then using the transformer model to build to replace sketches, as we call them LLM sketches. Maybe that is possible, right? But you making maybe that is all more universal type of sketches can answer many questions, right? I hope that someone can build that part. But but as the common challenge right now is that how to explainability of that is hard, and then how to really generalize to different traffic, different aspects, as the traffic is very dynamic at the moment. And my setting, there's some successful cases on other domains, but I still feel like networking traffic is very high dimensional. It's very hard to capture. Still, that make it a fundamental challenge. Yeah, sure. Yeah, you can say something.
Yeah, no, I completely agree. I think that so we have networking for AI and AI for networking, and I think that I've seen some works on telemetry for AI in terms of getting the networking to work better for AI traffic. But yeah, I think that using LLM to do better telemetry will. I think it's going to be a different kind of structure, and probably. I mean, thinking about the current constraints of programmable hardware, I don't quite see how that will work. But on the other hand, we do see we are seeing new kinds of programmable hardware that are more flexible and that are less constrained. They still have constraints because if you want to run at line rate, there's only so much you can do. But I think that once we start understanding what we can do within these new types of programmable hardware, then I think we might be able to answer these types of questions in a better way.
I see. Yes, we're already 5 minutes past our scheduled time, but I do want to ask one final question to both of you. So this is a very comprehensive survey, and in the paper you list several future directions. But my question to each of you is, what is the most exciting direction you want to tackle? Like suppose you only have time, or the immediate which specific topic you feel most exciting about along the line of data structures or in telemetry for each of you.
So yeah, I think there's a lot of really interesting directions that we're looking at and that I think are still to be researched. For me, I think this looking at these new types of programmable hardware and understanding their architecture and seeing what kind of telemetry, how can we improve existing telemetry methods using these new types of hardware, and basically, can we do new things with these types of hardware? I think that for me is kind of one of the main questions that I think I'll be looking at in the next few years.
Cool. How about you, Alan?
As Shir said, I think we list out several future directions. But myself, right now, I think it's very excited about we have more and more such network hardware coming out, right? And I think our whole community has a vision, not only just company and the universities. We want eventually it's the AI managers networks, right? We cannot deny that. It's probably AI will currently helping our engineers to manage the network faster or detect the problem faster. Right. At some point, that it still be like AI playing what kind of roles of the whole autonomous networking management, right? So I wanted to rethink about with so many different network. It's kind of bottom up still, right? We have understanding of so many different hardware, and we have so many characteristics we can capture and understand, and then we should kind of go back to think about more like top down now. Like I want to complete this whole task of detecting a specific tag on this whole loop. What is still missing here? Like it's missing some we cannot zoom in a particular traffic to understand certain part, or we are missing the support for our hardware, or we are missing right machine learning tools that are being applied. I think for me, it's particular want to spend time on this whole loop think about all this, the 3 steps of what's being missing there, and then spend time to kind of even we cannot solving this problem entirely from beginning, then can we demonstrate a whole loop by 1 case or 2 cases completely? I think right now we're spending a lot of each of the step we have a lot of efforts, and but linking them together has been kind of missing out right now. Yeah, but of course the AI capabilities and it's improving such dramatically. I think we should kind of but we provide a fundamental or observability to the network where we should ask what they need.
I see. So basically, Shir's most exciting part is about how to understand that all these new emerging new hardwares in the network. How can we leverage them to perform telemetry in a maybe more efficient or accurate, basic how to perform better telemetry, right? And Alan's most exciting part is about how, since we already have several pieces or many pieces in this area, how do we glue them together to form the whole loop? Basically, not only to put just telemetry, maybe telemetry, operation, maintenance, diagnosis. Basically, try to build maybe in certain ways leverage AI to help close the loop to automate the whole process. I don't know if I interpret
right. Something along this line, but I think our vision is like that. But I think it's could be step by step, right? So we have we have a using security paper that we talk about. Hey, we can define a large number of DDoS attack as a switches that it has multiple different components, right? Everything is menu. Everything is a hacky of configuration that we put on, right? Yeah. So like I want to show that once our telemetry tool detect this traffic, I can see a clear reporting of this results, and then figure out by maybe ILM that give me a configuration, say, hey, this is the strategy that you need to apply the rate limiter, and this rate limiter could be applied to the switches. And as host said, if I can make this 1 case example, I would be very happy to report. But right now, this whole part is it's a human being and a research prototype.
Definitely, yeah. We can talk more about this in Portugal, I guess, in September. Because one thing we are trying to look at, I mean, just a very timely advertisement. Maybe one thing we are trying to look into is, can we use large language model based, or trying to integrate some formal methods together, basically formal logic stuff, and try to automate the whole innovation process. Basically, like what I think I have one slide in HotNet 2023 saying maybe one day we can have a large language model to help us design system and write papers for us, and then we can all lay back and enjoy.
I hope that is not true, right?
I know it's hard. I know it's maybe too wishful thinking, but yeah, maybe. Yeah, I think there may be some silver lining there. We can try to. Yeah, we can talk about more offline.
Just to say one more thing, I think like the one of the high level goals that I think have been the case from, you know, when programmable networks started coming out is these self-driving networks, having the networks run themselves. And I think we're taking this step by step. And
Exactly.
I think a lot of the things we've discussed today are kind of, you know, steps in that direction, hopefully.
Yeah, definitely. Yeah, we should get together to write another position paper in the future. Yeah. Cool, very cool. Yeah, I know we really enjoy the discussion here, but unfortunately we already like 10 minutes over our scheduled time. I know Shir and Alan, you each also have other appointments and have other works to do because I haven't finished inventing this AI automated paper writer robot for yet, right? So unfortunately we have to adjourn this meeting. But I think this is to me, and I believe to all the audience here, I think it's safe to say that we learn a lot from about telemetry from the presentation, and we also try to learn about research and future, in particular future research. Lots of potential future research topics from our discussions with the author. So this is a very productive discussion, and so I'm. As an organizer, again, I said I have to call it a night or call it a day. But I want to thank Shir and Alan and Lou again for the wonderful discussion and the presentation. And it's really wonderful for you guys to take the time to do this. It's really would really benefit our community, because we will later not only we do this live broadcasting, we will also put our the video to YouTube. So and then we will let the community know. And so yeah, I think I already finish all the words I can think of because it's past midnight. I'm a little bit sleepy. So okay, yeah. Thank everyone again on the meeting, and it's really wonderful discussion. And I hope to see many of you 2 weeks later for our next meeting. All right, thanks,
Thank you so much for having us.
Thank you for organizing this.
Thank you
Bye.
so much. I appreciate it. Thank you. Bye, everyone.